Super papillo.
It looks like a pig.
Pig, right?
Yeah.
I feel it.
Where did it get from? Pi of c equals pi. Frequency is system.
Okay, let's take the last part of the course. I find that you really have to cover lots of ground in this last part. There's so many examples, so many complicated things to do that I don't think I can do all of them, but we try to cover as much as possible. Okay, so you have section 9.2 that we went through, which is about impulse function. Okay, the impulse function can be thought of as a limiting case of the derivative of a step function. So when you have a step function, you can think of an approximate step function or unit step function that looks something like this. And then you differentiate this, you get something that looks like that. Okay, I call this an approximate impulse function. And this is delta. The height is 1 over delta. And you can also do something slightly different. Instead of defining the approximate step function as something like this, you can also define the approximate step function as something that looks like this. Okay, so that this width here is delta. In the book use epsilon, but it's the same thing. Okay, and then the height is 1. So when you differentiate this approximate step function, you have something that's centered. You get an approximate impulse that looks something like this. And then the width of this is equal to delta, and the height is 1 over delta. Okay. Either one is fine. You can think of the impulse function as the limiting case of the two functions when delta goes to 0. When delta goes to 0. Okay, are there any questions about what the impulse function is? Okay, you can be thought of as that, and then you can also have a diagrammatic representation for an impulse, and it will just look something like this. You just draw it with a big arrow, meaning that it goes to the root. Okay, it is an infinite function. You can also have a doublet, which is defined to be the derivative of the impulse, and usually you represent the doublet like that. Okay, if you differentiate an impulse, if your impulse looks something like this, this is actually what you would see in the real world. Okay, you can make this in the real world, but it's very hard to make that in the real world. Okay, so we differentiate this, you will get something that looks like this. So this is approximately the doublet in the real world, which you can diagrammatically represent as such. Okay? So let's do one example from section 9.2, which is example 9.13. That you have the transfer function, which is called a frequency response in the textbook, f1 plus j omega. Okay? And that if you have a transfer function that is describing this LTI, okay, if you have an input, then you have an output, y of t. Okay? And then you can take this back to the time domain. Okay, you can take this back to the time domain and repeat this calculation in the time domain. The input in this case is taken to be a rect function. Okay, a rect function can be written as the sum of a unit step function minus another unit step function that is shifted. Okay, there's another way to write the rect function. And then if I Fourier transform this, I get what is known as the impulse response. Okay, I get what is known as the impulse response. And then the output then is equal to the input f of t convolving with the impulse response. Is this fact clear to everybody? Is this clear to everybody? It's clear, right? I can quickly rederive that if you want to. So if you have h of omega, if you have a frequency domain signal, either j omega t coming in, then your y of omega will be equal to f of omega times h of omega e to the j omega t, right? This diagram you can understand quite quickly. Now if you Fourier transform this diagram, okay, and over here you get this in the time domain. You Fourier transform this, you get that. You Fourier transform this, you get the time domain version of that. And if you Fourier transform this, you get the time domain version of this. But f of t is just 1 over 2 pi minus infinity to infinity d omega f of omega e to the j omega t. Y of t is equal to the Fourier transform of this thing, the omega f of omega h of omega times e to the j omega t. A product in the Fourier space corresponds to a convolution in a time space, in a time domain. Okay, so if you make use of the convolution property that we have learned before, then this just says that yt must be f of t convolving with h of t. This is just a convolution property. So we get this result over here. Okay, so let's do this more properly. And that you have to be aware of the fact that you know how to Fourier transform this quantity. Okay, you know how to Fourier inverse transform this quantity. You have to know how to do this. d omega e to the j omega t. H of omega is just 1 plus j omega. Okay? But that is kind of hard to do. So you do a textbook lookup. You do a table lookup. That is the easiest one to do. Okay? We know this for a fact that if you have a function ut e to the minus t, and if you Fourier transform this quantity, okay, if you Fourier transform that quantity, and almost everybody knows how to do that, okay, this thing Fourier transform to 1 plus j omega. To Fourier transform this quantity, okay, just perform this integral. This is h of t is equal to that. And then if you Fourier transform it, then you have h of omega must be just dt u of t e to the minus t e to the minus j omega t. And then this is the step of Fourier transforming. Okay, since this is a unit step function, you will truncate the integration so that it's 0 when t is less than 0. This just becomes a semi-infinite integral. And now you can remove the unit step function now, because it's always 1. And then you can consolidate these two together. You get 1 plus j omega t. And when you integrate this, you get 1 over 1 plus j omega. Okay. So if the Fourier transform of this is equal to that, the inverse Fourier transform of that is equal to that. That's how those lookup tables are made. Okay. How to do this in closed form, you have to know more mathematics. You have to learn complex variable theory. Then you can do this in closed form. Okay. At this point, you cannot do that. So you just do a table lookup in Okay. So the next thing in this example is to actually do this convolution. Okay, convolution y of t then is equal to u of t e to the minus t, which is my h of t, convolving with the input. The input can be written as u of t plus half minus u of t minus half. This is just my rect of t. Okay, is this clear that the rectangular function, which is a box function, can be written as the difference of these two functions? Is this clear to everybody? Okay, this is great, and you have this by the distributive property of convolution. You can distribute this over two of them. Okay, minus u of t convolving with u of t plus half, or t minus half, sorry. T minus half and t plus half there. Okay? Then, if we define a quantity that is equal to this thing convolving with u of t, okay, then this thing over here is just this thing being delayed. Okay? This thing being delayed. And when you delay this, let me revise this property with you again to make sure that you're cognizant about this property, that if qt is equal to that e to the minus t convolving with u of t, what is qt plus, or qt minus tau, say, or qt minus t0, say. What is this equal to? This is one of the shifting property of convolution. Then it will be equal to what convolving with what? You delay either one of the two. You don't delay both of them. Okay? So this is equal to ut minus t naught e to the minus t minus t naught convolving with u of t, or you delay the second one convolving with u t minus t naught. Either one of this is correct. Okay, but you don't delay both of them. And this convolution notation is actually quite confusing, yes sir?
I'm wondering if you delay both of them to like half of t naught, then would that
No, it still wouldn't work. Okay, it still wouldn't work. I don't believe so. You can try. Okay, but I don't think it will work. Does it work? Maybe it works.
Do a proof.
What is that?
Do a proof.
Yeah, I can prove it, but maybe it works. Okay, I can prove it other pathway. Okay, but let's assume that this is what we have in the textbook. Okay. So I want to I want you to warn you of a very confusing notation that you have in your homework. Okay, this is actually a very confusing mathematical notation. Okay, it doesn't mean that Q of 4 is equal to F of 4 convolving G of 4. This is utterly wrong. Okay? This is utterly wrong because that doesn't mean that. Q of 4 means you first write this explicitly as a convolution integral f of tau g of t minus tau d tau, and then evaluate this at t equals 4. That's what it means. And it's very different from the meaning of this. Okay? So I think you have a homework set to do that. And I hope you don't get confused by the notation. This is actually a very confusing notation. And some mathematicians would prefer to write it in this manner. Okay, to explicitly say that the t does not belong to f and g. It belongs to the result of having two functions operated upon each other. Okay? So, I just want to alarm you of the fact that when you delay one of them, it doesn't mean that you delay both of them, because this is a rather confusing notation. It actually means this or that. You can go through the details, and it has been derived. So because of this, then I can say that this thing is actually qt plus half minus qt minus half. Can you see that? The second one I can call it qt minus half. The first one I can call it qt plus half. Then I only need to do one of this convolution and use it as a template or a cookie cutter template that you can use to derive the two terms. You see my point? Okay, I write this as the difference of two terms. I notice that the standard of the unifying expression between these two terms, that both of them share something with q of t. If I know how to find q of t, I can write my y of t being equal to that. Okay? Can everybody see that? Okay, I see nodding heads. So that is very good. Okay. When I see nodding heads, I'm very happy. So let's find q of t then. Q of t is equal to that. Let me use this part of the blackboard. Q of t is equal to u of t e to the minus t convolving with u of t. So if I write this out using the meaning of this mathematically, then this will be something like this. Minus infinity to infinity. Okay? Then I know that when tau is less than 0, this forces the integrand to go to 0. When tau is larger than t, this forces things to go to 0. So I can set the limit of integration to be that and then drop the unit step functions. I only have that integral to do. Okay, and if I do this integral, I have minus e to the minus tau 0 to t, which is minus e to the minus t. So that is at least my q of t. Okay, and to be more precise,
There should be a +1.
Yeah, I think
What?
there's a plus
Plus
one
one.
after that.
it's a +1.
Because you plug in
Oh yeah,
0,
yes,
you
yes,
get a
you're
1.
correct. Okay, there's +1. Okay, and what do I have to qualify the answer with? What happens if t is less than 0? If t is a number less than 0, what happens to this process? If t has been a number less than 0, or t here has been a number less than 0, what would I have got? I got 0, right? So I should qualify this answer with the fact that it is 0 if t is less than 0. So I have to put a unit step function over it. So that is my q of t. Okay? Then you add these two functions together. My y of t would be just that two functions. You can add them up, okay? You shift them and then you add them up, and it just gives you the plot. The plot. Okay, the plot looks something like this. Okay, you have to put a negative sign on one of them, a positive sign on the other one, so the plot looks something like this. Okay? And then this is y of t. It consists of shifting this function and then subtracting this function again. Okay, so that they actually subtract each other, and it will go something like this. Okay? So this is example 9.13. Okay, are there any questions regarding this? And then let me just revise all these convolutional properties. And there is a table 9.3 that you have to study, and you have all the convolutional properties. I think we went through all of them. Okay, we went through all of them, but I just want to mention that the scaling property is written as such in the table, okay? Whereas I might have just have assumed A to be positive, and in my lecture I might just say this, okay? But if A is negative number, it doesn't matter because delta x or delta t is an even function. Okay, because it's an even function, you can put an absolute sign over your A, and you go to the derivation, and that is a scaling property. Okay, and the other properties, you can study this table and understand them. So, so since there are so many examples in this section, I just select some examples and do some, and not all of them. Also, let me do example 9.17. Okay, example 9.17, and see. You're given the fact that y of t is equal to t squared u of t. Okay, you can do this intuitively, or you can do it mathematically. Intuitively, you'll say that if I plot this function, it will look something like this. What is this function equal to when t is less than 0?
0.
It's 0, so it looks like that. And then when t is larger than 0, it has a quadratic behavior, a t squared behavior. Okay, is what it says. So the book asks you to find the derivative of this function. Okay, and you can intuitively realize that this function, the derivative of this will be 0. But over here, what does it become on the right hand side? 2t, right? Just 2t, very good. The linear function of t. So the answer must be that b, let me write it up here, since it might be too low down for some of you to see. So I can actually write it down here, 2t u of t. Okay, this is my intuitive answer. Okay, it must represent this function. So, but if I don't like intuitive way of doing things, I want mathematics. I want to go through all the mathematics that I know and mobilize my knowledge and check if I get the same answer. I can also do that. Then yt is equal to t squared ut. Okay? According to my mathematical knowledge, is the differentiation by parts. So I can think of this as product of two functions. When I differentiate product of two functions, I differentiate the first one, keep the second one constant. Okay, I get 2t ut using the product rule of differentiation. And then I do the second part, which is t squared du t dt. This is the product rule. But what do I get when I differentiate the ut dt? The direct delta function, very good. So then I have 2t ut plus t squared delta t. Okay? But you have one more knowledge to invoke, which is that f of t multiplied by delta t is always equal to what?
T.
What?
Ft.
F of
0.
t equal to 0, and don't forget this thing, okay, equal to that. Okay, that's, I think, called the sampling theorem, okay? For f of t, delta t minus t0 is equal to what?
T naught.
F of t naught, very good, times delta t minus t. In other words, those coefficients that are multiplying your delta function always becomes a constant. Okay? So if you were to invoke this principle, what happens to the second term?
0.
It goes to 0. So this is equal to 2t u of t. The same answer as you have obtained over here. Okay? So this is a more mathematical way of deriving the answer.
But why do you want to claim that f of t del t is equal to f of 0 del t? Why do you want to multiply by del t again? It's just
Which
equal to f
part
of
is it?
0, right? F of t del t is equal to f of 0. Why multiply
This
by...
is equal to that, right?
But why multiply by del t again?
Well, if I were to plot this on the left-hand side, well, how would this look like? F of t delta t. It is infinite right at the origin, and the infinity is multiplied by f of t equal to 0. That's how this function looks like. And then 0 everywhere else. Right? If I drop this delta t, how would the right-hand side look like? A constant function. It's wrong. Right? And now if I plot the right-hand side again, it's something that goes to infinity, right? T is equal to 0. 0 everywhere else. But the height of this infinity is multiplied by f0. So it's the same as that one over there. So I need to keep delta t on both sides of the equation. Okay, to make it buoyant. Okay? Any other questions regarding this? If not, then let's see. Yes?
Is this like delta t property can be used as the convolution? Like the way we talked before, like the convolution, like f omega times h omega, like tau times h tau, ain't that like the same property? But is this delta t property can be used as?
So delta t can be treated as a function. In our course, okay, delta t can be treated as a function, and all the convolutional properties you have learned between two functions can be applied to delta t. Okay, don't have a fear of that. Even though it's not a proper function, okay, mathematicians are not too comfortable with it. So it's now called a distribution function. Okay, so all the convolutional property that you have, like delta t, what is the Fourier transform of delta t? Maybe we can think about that. So if we were to Fourier transform this, then we would multiply by this, and then integrate over t, right? What does this give you? 1, right? What is the Fourier transform of delta t minus t naught? It will be this quantity over here. And what does this give you? What does this give you? Using the sampling theorem, sampling property of the delta function, it will be equal to that, right? So remember we learned this thing. If f of t Fourier transform to f of omega, f of t minus t naught Fourier transform to what? The shifting property of convolution. Okay, very good. Okay. I'm so happy to hear a chorus coming from you. Okay. So all of you know this by heart. So you see that shifting property, the delay property of convolution is still there for delta function. Okay? So okay, let me do example 9.19. Okay, example 9.19. There are too many examples to do in this textbook. but let me do example 9.19. But maybe I should go over one more property of the other function. Okay, that we know that f of t convolved with h of t is y of t. Then from the convolutional property, again this is very misleading. Okay, this is very misleading as a notation. But if you were to find the derivative of y of t, what did the convolutional property tell you? How can I evaluate this using what? I can differentiate one of them, okay, convolving with h of t, and then I can choose not to differentiate the first one, but differentiate the second one. Okay, this is what I learned as a convolutional property of derivative. And now if delta t convolving with h of t is my y of t, if I were to find the derivative of this now, then this is equal to either delta prime of t convolving with h of t, or the same as equal to what? What is the other choice that I have?
Delta t convolve with
Delta t convolving with the h dt. Okay, but this second convolution can be evaluated even when you're blindfolded, right? What is something when you convolve with the delta function? It is just itself, right? Okay? So we have this interesting property that when a doublet convolves with the function, it always gives the derivative of the function. Okay, it always gives the derivative of the function. That is a special case about a doublet. Okay? So this is something that you might like to know. And why is h of t called the impulse response? H of t also has a special name. It's called the impulse response. Okay? So what this describes here is that if you have a box, LTI box, and if your input is f of t, then the output is yt, which is equal to f of t convolving with h of t. And then this h omega Fourier transform to h of t. Okay? So this is the picture you have. And I have proven this point over and over again. Okay? But now if you have delta of t coming in to this same box, it will be delta of t convolving with t, and what would be the output? Using the property that convolution of a delta function with another function, you know, like the back of your hands. Okay? So this is just equal to h of t. So when you have an impulse as an input, the output is just h of t. That's why this is called the impulse response. Okay? So let's do example 9.19. Yes?
How come you can't just keep differentiating the delta function?
You can? You can if you want to.
Would it continue to do that derivative property if you keep adding primes to t?
You will have to keep using integration by parts to evaluate it. Okay? Because the other functions are very strange functions. They are extremely sharp. If we differentiate, they become even sharper and sharper.
Since like the doublet is from all the way to the top and then all the way to the bottom, if you keep doing that, eventually lead to some
Right, so you actually visually in your mind a function that flips back and forth at the origin, and mathematicians don't like that. Okay, it's not a function anymore. You can think of it as a distribution. And let me tell you what the meaning of a distribution is. A distribution has no meaning by itself unless you multiply by a function and integrate. Its meaning is defined by its integration rule that you apply with another function. So like, one way to define what a doublet is to define this outcome. Okay, since this is a distribution, I cannot draw it. When you draw it, it's very difficult to draw. You can think of it as a limiting case of this function. And if you can differentiate it one more time, you can think of it as maybe something like this, like this, like this, like this, and then take a limiting case of that function. But it's very hard to draw this function. But mathematically, you can define this property by defining what this outcome should be when you multiply by that, okay? And then we did integration by parts before, right? This is a product of two functions. So using integration by parts, you integrate the first term, you get delta t, because delta prime t is defined to be the derivative of this. And then you evaluate it at two endpoints, and then you now take this integration, and then using the rule of integration by parts, then you have to differentiate the second function, and then you have to put t prime here. It doesn't matter, and then integrate this. Okay. The second integral can be done in closed form because we know how to do this blindfolded, right? Because it's just multiplied by a delta function. The first term evaluates to what? 0. So you have 0 for the first term. The second term is just the f dt, and t is equal to 0.